Alright, in this video I'm going to go over the notes on Newton's first law. Actually, this is a PowerPoint with Newton's 3 laws of motion. Today we're just going to mess with Newton's first law and talk a little bit about free body diagrams. So we would be amiss to talk about Newton's first law, or really to go through any physics course, without mentioning Isaac Newton himself first. He's extremely important to the field of physics. And not only physics, he was also a mathematician, he was an astronomer, he was a philosopher. He had quite an extensive law career as well, because people in his day kind of tended to be jacks of all trades as opposed to specializing in one particular field. But he's maybe most noted, well, maybe not most, but he's very highly noted for his works in physics. One of his most notable accomplishments is that he did play a major role in the development of calculus, which is pretty crazy when you think about it. For us, we'll focus on his law of universal gravitation, which we'll talk about later, and then the 3 laws of motion, which we're going to talk about this week and next week. Those are the foundation of classical mechanics, which actually we've been talking about since the very beginning of the school year, and you didn't know it, but the work that he did formed the foundation of all of the description of motion that we've been talking about since then. So that's Newton. Newton talked about forces, and if I asked you what a force was, you might be able to tell me that a force is simply a push or a pull that's exerted on an object. Forces do have magnitude and direction, which means a force is a vector as opposed to a scalar. Just to review those, remember that vectors have both magnitude and direction. A scalar only has a magnitude, and if you can't remember what the word magnitude means, it's just the number. If I say that I'm going 30 miles per hour north, the magnitude of that vector is the 30 miles per hour. That's the size or the amount. The units of force are newtons. They're named after Isaac Newton, and in science, when we name a unit after a specific person, we use a capital letter. So newtons also always have to be symbolized with a capital N. Some specific examples of forces. First, I will list what we call contact forces. Some examples of those are friction, tension forces, the normal force, thrust forces, which come from engines, spring forces, and what we call an applied force, which is simply pushing or pulling something. And I know you may not know what some of these are, but I know you know what most of them are. We'll talk specifically about some other ones. And then we have non-contact or long-range forces, and a few examples of those are the gravitational force, gravity, and also the electromagnetic force and the magnetic force, which we actually won't get to in this class until the second semester. But I want you to look at the forces that are listed here and consider to yourself real quick, pause the video if you need to, consider what the difference is between contact forces and long-range forces. Alright, if you thought something along the lines of the fact that these forces over here, contact forces, all require physical contact to be in action. That's why they're called contact forces. And then these over here do not require contact to be in action. And so that's the basic difference between a contact force and a non-contact or a long-range force. That may seem like a very mundane thing to you, but the reason why I bring it up is it's interesting to consider in physics. Not only the difference between these two, but the quite interesting concept of a long-range force, for instance, gravity. I hope you don't do this, but the next time you step off the side of a building, you will not be in contact with the earth immediately, but you will be eventually, because gravity still works on you even though you're not in contact with the earth. And I don't know if you've ever actually thought about this before, but you could drive yourself crazy trying to figure out how gravity actually works. And that's a question that a lot of physicists ask. It's an answer that nobody really knows. Gravity is an interesting thing because nobody really knows how gravity or the earth can reach across space. It could be empty space even, there doesn't even have to be any air there, and pull you toward it. Gravity doesn't have a brain. It doesn't know you just stepped off of that building. It's very interesting, and it's sort of a mystery how masses attract other masses, and other long-range forces the same way as well. These are quite a bit more interesting than these, because we tend to understand contact forces pretty easily. We understand that if we push or pull something, it will move if we apply a large enough force. So contact forces, long-range forces. Specifically, I want to talk about tension first. The tension force is applied through all ropes or chains, like backpack straps, purse straps, any long, thin object that is applying force to another object or supporting another object. There will be a tension force there. Rubber bands, tension force. Another force, common, very, very common force, is called the normal force, and it's not called the normal force because it's, normal or abnormal. Normal refers to the fact that it's perpendicular to any surface. The word normal means perpendicular. So it's a force that's applied to any object that is sitting on a surface. So any object that's touching a surface has a normal force. In other words, in every instance that we talk about where there's an object sitting on a surface, there's going to be a normal force going on that will be perpendicular to the surface on it. So if you look at the picture of these boxes, for instance, this box here is exerting a normal force on this box, and that normal force is exerted upward, and it's exerted perpendicular to the surface of the box. And the normal force will act to counteract the force of gravity that is pushing down from this box here. In other words, if the normal force wasn't there, this box would fall through the entire stack. So the normal force acts to keep the object actually on the surface and not falling through. Frictional force. Friction force you know a lot about, and we're going to discuss it in way more detail a little bit later, but basically what you need to know now is that friction forces will always be applied opposite the direction of motion. So if you're moving in a north direction, frictional force will be applied toward the south because friction wants to slow you down. Weight. Your weight is also a force, and this equation you need to write in your notes. It's W equals mg. The W is the weight, and that is a force, so it must be in newtons, capital N. Mass. This is the first time that we've dealt with mass this semester. And remember, and I would circle this if I were you, that masses must be in kilograms when we enter them into equations. So if you have something in grams, it needs to be converted to kilograms. And then G is actually the acceleration due to gravity, which we know now to be 9.8 meters per second squared. It was A when we were dealing with kinematics. Now it's going to be represented by G, at least with this specific equation. This equation, W equals mg, you might also see Fg equals mg. F sub g is what you might see. And F sub g simply stands for the force of gravity. You'll see that if you look on your equation sheet, actually. Equation number 10 on your equation sheet says Fg equals mg, the force of gravity. Same thing as weight. Okay, Newton's first law, let's go ahead and roll right into that. But you need to know that Newton's first law is also sometimes referred to as the law of inertia. All right, so let's just review the concept of inertia, which I know you've been exposed to before. Inertia is simply the tendency of an object to resist a change in its motion, any change. And that can be a change in direction or a change in its speed. And that includes objects that are at rest as well. And so a simple illustration that you can think about in resisting change in motion, imagine that you're stopped at a stoplight, you look in your rear view mirror and you see some vehicle hurtling toward your car at like 60 miles an hour, and it's obvious they're not going to be able to stop. And the question is, would you rather that vehicle be a big semi-truck or a motorcycle? I think all of us would obviously choose the motorcycle, even though we'd be sorry for the guy riding the motorcycle. The point is, the motorcycle gives you the least chance of actually getting hurt in the accident. And the reason is because, quite obviously, the motorcycle doesn't have near the mass that the semi-truck does. And if we relate it to inertia, both of those objects are going to change their motion. Both of them are going 60 miles an hour. They're both going to stop eventually. The question is, which one has a greater ability to resist the change, to resist that change in motion? Well, that's the semi-truck, because it has a lot more mass, which brings us to the next point, that inertia is directly related to the mass of the object. And I want you to make a separate note right here in your notes, and make a note to yourself that inertia is not related to velocity. Inertia is not related to velocity or speed. So I don't want you to get this concept confused with momentum, which we'll talk about later. Momentum brings into it the concept of speed. Inertia has nothing to do with speed, it's only mass. So if you have this semi-truck that we've been talking about, the semi moving at 5 miles an hour and the semi moving at 50 miles per hour, which one of those has more inertia? Well, since inertia has nothing to do with speed, they both have the same amount of inertia. In other words, both of them have the same ability to resist a change in motion, because inertia doesn't have anything to do with the speed, even though the speed is different. So mass. Mass is simply the amount of stuff that an object has. And hopefully you know by now that mass is the same everywhere in the universe. Whether you go from here or to the moon or anywhere else, you have the same amount of mass, unless you like cut off a leg on the way to the moon or something like that. You have the same amount of mass. But what is different from here to the moon is your weight. Weight is a force that depends on the acceleration of gravity that you're subjected to. It's 9.8 here on Earth, and it's 1.6 on the moon. The big point is that the more mass an object has, the more inertia it has, very simply. In other words, the inertia is directly related to the mass of an object. Once again, inertia is not at all related to an object's speed. That's the law of inertia, which again is basically the same thing as Newton's first law, which officially stated is this. This is what Newton said: every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it, which may sound very complicated, but the way that you've always heard it sounds more like this: an object at rest remains at rest, and an object in motion remains in motion. And this happens unless that object is acted upon by an unbalanced outside force. And when you write that down, I want you to underline or circle these two words: unbalanced outside force. To define the word unbalanced, I want you to picture a tug of war game between two people. And if one person pulls with a 50 Newton force to the right, the other person pulls with perhaps a 20 Newton force to the left. Quite obviously, the 50 Newton force is going to win out, and the whole system will move to the right. It was standing still to begin with, and it will move to the right toward the larger force. That's an unbalanced situation. We have one force going the other way, and it's not counteracted by an equal and opposite force. Whereas if both people were pulling in opposite directions with a 50 Newton force, I think it's easy to see that that system would not move. We would get no movement of the rope or the two people. That would be a balanced situation. So the force has to be unbalanced to cause a change in motion, and the force has to be an outside force. And to illustrate what an outside force means, imagine again that you're in your car, you're driving down the road, and your car breaks down, and you kind of feel stupid because you ran out of gas. But you see a gas station up ahead, you want to push your car to the gas station. And it might be kind of funny if you drove by somebody and you observed them trying to push their car from inside the car. Obviously you can't do that. You can't push on your car from in the car because you're pushing on the car against the car itself. You're going to pull the car apart before you actually move it. Obviously you have to get out and apply an outside force to move the car. So the force that the force that will change motion must be unbalanced, and it must be an outside force. So that's Newton's first law. An object at rest will remain at rest, and an object in motion will remain in motion. And I don't know what you're thinking at this point, but I'll be honest with you, when I first heard Newton's first law, I really thought that it was untrue. I thought it was kind of crazy, because in my experience, Newton's first law doesn't really work, because here on Earth, objects in motion, at least in my experience, don't tend to remain in motion. For instance, when I'm in my car and I take my foot off the gas pedal, the car doesn't remain in motion for very long. It tends to come to a stop. And so the question I've asked myself is, why don't objects on Earth remain in motion forever? And the answer to that question is simply friction. Friction is what we have on Earth, and there's absolutely no way to get rid of it on this Earth. So it's not that Newton's first law is not in effect on the Earth, it's that we always, in every single situation, have an unbalanced outside force acting on us. And that unbalanced outside force will always be friction. For that reason, it's almost impossible for us to actually experience this uniform motion that doesn't change, because it's not acted upon by that force. But we can certainly think about it, we can talk about it, and we can understand what it means. In most of the problems, we get to neglect friction, but sometimes we won't. Sometimes we'll consider it.